So welcome to the second lecture of the mini course on the Topos approach, and I actually see a few new faces, which is good. Instead of a few other people, this was to be expected. Today I will continue what I started last time. Well, first I gave this big introduction, what it's all about, but now we want to look at certain parts of function analysis that we will need in the Topos approach later on. Of course, function analysis is vast, and I can just give a very small selection of things, and there will mostly be no proofs, which I apologize, but it's just a matter of time. So we'll talk about some things, and I will try to give you some kind of intuition what these objects are about, and I think it's necessary because we'll see lots of definitions, and the main task, of course, is getting an idea what it's about, and some things may be very familiar to some people, but it's actually aimed at people who have maybe not heard in detail before about Hilbert spaces, Banach algebras, linear operators. So, I think I'll write on the whiteboard. I have it on slides, and I'll send around the slides later on, so you don't have to take notes if you don't want to, but of course you can. I just think that seeing the thing develop on the whiteboard is probably more productive than just seeing a slide. It's usually too quick. My standard reference on these things is the following book. And Ringrose. It's called Fundamentals of Theory of Operator Algebras. This comes in several volumes, but what we'll be talking about is all in volume 1. So, of course, you can find proofs of everything I'm saying today in this book and in many other books, actually. But this is actually the best way to get this book, which I have it with me, is as an AMS reprint. This was originally Academic Press 1983. So if you want to have a look, just pass it around. But the AMS reprinted it in 2000, and that's not too expensive. Actually, there are 2 volumes and 2 further volumes where they just have the solutions of the exercises. So you can guess it's a massive subject, and we will, as I said, pick a few things. Last time I said what a pre-Hilbert space is and what a Hilbert space is. So of course most people are familiar with that, but there may be people who are less familiar with it. Should I repeat this just to get things in place? I need some kind of answer here. A pre-Hilbert space, yes, okay. Maybe it's a good point actually, because we will talk about completeness a bit. So let's start this definition. I think I need another pen. So, points the following. So let's call it E. trick. So, and the main point is it's a vector space of a field with product, also called scalar product, which is a mapping more or less times E into the field. I must be careful. Sometimes use F, sometimes use K. So we have K from German Körper, which is the one. Anyway, you find this in some function analysis books. Okay, it's such a mapping, taking two vectors into a scalar, the following properties, such that first thing is for all lambda and mu k and for all x, y, z in E, you have that x comma lambda y plus mu z equals, let's write it here, lambda times the scalar product of x y plus mu times the scalar product of x z. So, and this is of course a convention, we have linearity in the second argument. Mathematicians very often have by convention linearity in the first argument, physicists usually have it in the second, so we'll go with the physicist convention. That's the first thing. The second thing is for all x and y, you have that, well, y is complex conjugate, and this makes clear why we would like our field to be R or C. If it's R, this becomes trivial, but if C, it's C, it means something. And the third property, of course, is for all x in E, we have that x comma x is greater than 0, and we have x equal to 0 if the order x itself is 0. Okay. So people who know Hilbert spaces, of course, know these things. So why is this just free Hilbert space? We didn't say anything about completeness yet, so we have to do this by hand. And so the definition is a Hilbert space, as usual, this gets this categoric H. Hilbert space. It's a pre-Hilbert space. That is complete in the norm. So, which is also to be defined. So norm of x is the square root of x comma x, which makes sense, of course, due to the third property. So I can form this. There's actually quite a lot happening in this definition. First of all, we define a norm from our scalar product, so we can measure the length of vectors. So as I said, I want to give you some kind of geometric idea. And as I said, the norm is there to measure the length of vectors. We'll see a few examples of Hilbert spaces in a minute, and you'll see a very familiar norm showing up there in these examples. But once you have this, you can talk about convergence in the norm. You can define, once you have a norm, you can find the distance. Because what's the distance of two vectors? Let's say, this is just a side remark. metric. Distance function also goes from E times E into, well, actually, it of course does go into K, but we can be much more specific here. First of all, we know that the norm goes to the positive reals, which of course is much stronger than just saying it goes to our field. And likewise, the distance function will go to the positive reals, which I like to denote this way. 0 is included, so I make this explicit by writing R plus 0. And it's simply given by, well, d of, let's say, 2 vectors x and y is defined to be the norm of x minus y. Okay. It has the usual properties that, well, I could give you a list, but I think this is probably well known. We get a way to measure distances and we get a way to measure lengths. Actually, scalar product can do more, but for now this is what we can do with it, and we can talk about convergence. And if you have, I'll give you very intuitive pictures. I have your Hilbert space. As you'll see, actually R2 is a Hilbert space, so I can draw things on the whiteboard without actually cheating, because we can see this as a Hilbert space. So let's say we have a sequence of elements. So we have, let's say, xi, I have some index set, which, let's say, well, it's not actually important, it's countable, we can assume to be countable. And we assume that we sneak up to a certain point here, in the sense that the higher the index, the smaller this distance becomes, and for every epsilon that I want, I can find some index such that higher than this index, all elements in the sequence lie in a tiny ball of diameter epsilon away from our fixed x. So I can talk about convergence, but in a pre-Hilbert space, nothing guarantees that this point that we are converging to actually lies within the space. But now saying Hilbert space is complete just means every quotient sequence converges within this space. So the limit points actually lie in the space, as you would expect. But there's something going on, and of course there is a bit of simple analysis already at this point. So, okay. From now on, just by convention, our Hilbert spaces will be complex Hilbert spaces. It's just the usual thing in quantum theory. So convention from now on is K equals C. I guess quite a few things would also apply without any further difficulties for the real situation, but don't have to worry about this. Okay. I also introduced orthonormal basis. Orthonormal basis is a notion that I can define once I have a scalar product. Of course, I can talk about the basis of vector space right away, but now I have more geometry in the situation. So the idea is I want basis vectors which all have length 1, which is the normal in orthonormal, and I want them to be orthogonal to each other. So intuitively I want them to point in independent directions. And there's another convention, this is also, another convention is whenever I speak of a basis of a Hilbert space, I do mean an orthonormal basis. So let's write this down. Convention basis. just means that for all ij in this index set, so in set 1 to dimension h, we have that the scalar product of ei with j is chronic delta ij, which is 1 if I equals j, 0 if not. And this expresses the orthogonality, so that's the ortho part and orthonormal. And it's actually also the normality part, because this is 1, so this is the condition fixing an orthonormal basis. Of course, these are those things that you immediately show with your hands. If I ask you to show me a basis, then you do something like this. It's a good intuition that we will be using a lot, even if we talk about infinite dimensional situations. It's usually very useful to think about things you can show with your hands. There is a lot of geometry going on here. Okay, so it's time for a few examples, and of course you know them very well. Let's say the first example is, let's see, n, and that's basically it. I can of course also have C infinity, where I usually assume countable infinity, which just means I have a countable basis for my Hilbert space, which means I have a separable Hilbert space. So this explicit separable Hilbert space means as countable. Okay. I could give you a few more examples, but as you know, the vector space is completely determined by its dimension. So we have some extra structure here, we have a scalar product, but if we give you some other example, you can find an easy translation between the scalar products. So there's not much more than these examples, so it's really okay for now to go with them. We will see. Well, I'm saying it's always easy to find translation with scalar products. Of course, you have to think about this concretely, but it is true that the dimension still is the main thing, and we'll see one or two more examples later on. I should actually say how they become Hilbert space and what the scalar product is. In both cases, we have the following. We have that a pair x, y goes to something, but first let me rewrite this. I write this with respect to a certain basis. So this is a representation of x in the basis ei, and similarly I get something for I get something for y. The scalar product is the following. Just have some y. See clearly that it's linear in the second argument, antilinear in the first one, and we will see later on why it does not actually depend on the basis that we've chosen here. So for now, this may look a bit unsatisfactory because it involves a basis, and Hilbert space doesn't come with a preferred basis, but this definition actually doesn't depend on one. But it's a bit too early to show this. Okay, and the only difference in both cases is that, well, in Cn, of course, the index runs from 1 to n, and here it runs from 1 to infinity. But the scalar product is just the same. Okay.
In C infinity, do you restrict just to like the L2 sequences? Or?
Sorry?
In C infinity, do you just restrict to sequences which are somehow have convergent sum of squares? Or?
is that already the sequence AI and BI are such that well, a vector in this infinite dimensional situation is such that this becomes a square summable sequence, and likewise BI, and then also this product is actually fine. It's finite. It's
So
a good
what's
question.
the definition of C infinity then?
The norm is L2.
Yes, this is basically an L2 that I'm talking about here. Yes, that's exactly the point. Yeah.
Is it ever possible to have a basis where every element is expressible as a finite combination?
No, not in an infinite dimensional space. No.
Even if you use the axiom of choice?
Even so, because
It's not that you have a finite number of basis vectors, but you have an infinite number of basis vectors. So every element is expressible as a finite number of them.
no, the space is the linear span of the basis vectors, and this never allows me to exclude any trick.
I mean you're permanently excluding one. I mean,
Yeah.
every point you then express it as a
okay. I can of course find an orthogonal basis in which just the coefficient A1 is non-zero and all the others are zero. But in the same basis, of course, I have no guarantee that the coefficients BI, any of them, will become zero. So you can, of course, trivially do it for one of the vectors, which, well, you just pick a basis where the first basis vector points in the same direction as your vector. It just means A1 is non-zero, all other coefficients are zero. But there's no way to guarantee anything about the BI then, because you have to make
Isn't that one point here, just that basis doesn't mean basis in the sense of elementary linear algebra. It's that every point is a limit of finite linear combinations.
Yeah.
So it's the closure of the usual linear span of basis vector.
Yes. Yeah. Yes. Okay.
Oh, right, so second one it says accountable dense basis.
No, it has countable basis. And the algebraic
Think of the other
Oh, the
subspaces.
span
the
dense.
span
Yes,
is dense,
right.
yeah.
Okay.
The span is dense, yeah. So, okay. I already said a few things. I mean, let's define the linear operator, which, well, maybe just start from here. Linear operators can actually be defined between arbitrary vector spaces. So I'll write it down this. So we very soon concentrate on Hilbert spaces, but you don't need a scalar product, of course, anything of that kind. So linear operator. Let's call it A. Also, physics convention is that operators get hats, so I'll just use this. The linear operator A between here we can allow K again to be R or C. K vector spaces is, well, let's give them a name. Let's call them E and F. Is the mapping. Of course, such that we have for all x and y E that A apply to. And of course, sorry, I should also say for all lambda and mu in K. We have the following A applied to lambda x plus mu y is mu A applied to x plus, no, about a linear map. And as I said, we will mostly consider for us, we mostly consider operators from Hilbert space to itself. There's some things which are a bit more general. Okay, there is a notion of boundedness for such operators. So just a first remark, of course, if you see this as a function from E to F, this is never bounded unless it's just a constant. So we need another notion of boundedness. We want something which basically controls, if we start from vectors which are at most of length 1 in E, we want to see how far out can we be taken in F, so how much can vectors be stretched. And this is captured in the following definition. So operator A. I was already saying I want something of length 1, so I need more structure. I need a norm here to say this. So now I need a linear operator between normed vector spaces. Is called a bounded if, well, following thing, define the norm of A. This is supremum over the following set. Take all the AX for X of norm smaller or equal to 1. If this supremum is finite, so we define this thing, this is at the same time, this is called norm of A, and it should be bounded. Okay. That's very much the idea that I told you. So you take all the vectors within the unit ball, you look where they are mapped, and you should of course put a norm here. So you look how long do they get in where are mapped, and if everything within the unit ball is mapped to something of finite length, then you have a bounded operator. There's another notion we call such an operator continuous. Yeah, well, of course it should be continuous. Continuous map in the norm topologies. Again, just to give an intuition, the norm topologies are those which have little balls. Well, I can't define what a ball is once I have a norm because I can manage distances. So these little balls are basic open sets. So everything to get from unions of open balls. It's an open set in such a norm topology, and then you can of course talk about continuity with respect to this. Okay, and then there's the first non-trivial theorem, which I will not prove. It says that these two notions coincide. First of all, if you think about it for a second, in finite dimensions, there's no problem whatsoever. All linear operators are obviously bounded, and they're also obviously continuous. But in infinite dimensions, you do have unbounded operators, and pretty basic things in physics need unbounded operators for the description, for example, if you want to talk about position. So this is an important notion, and so the theorem, as I said, just has these two notions coincide. Yes. Where am I? Yes. Linear operator. A, E to F. Spaces is bounded if and only if it is continuous. Okay. This is maybe the first real instance. Okay, these convergence questions are also an instance where you see things happening in infinite dimensions they don't have to worry about in finite dimensions. But this definitely is a thing you don't have to worry about in finite dimensions. This is very typical for function analysis. Once you go away from the finite dimensional situations, you have a whole bunch of well, interesting structure there, but you have to work much, much harder than in the finite dimensional case. And so in some sense, function analysis is linear algebra in infinite dimensions, but that's giving the wrong impression, because the really interesting stuff is exactly what you don't see in linear algebra as you know it. Okay. So let me think what to do next. I wanted to say a few things about Banach algebras. I think that's sensible because that allows us to talk about the spectrum of an operator, which of course is the central notion. So let's do this. As I said, there's a list of definitions with occasional examples. If things are mysterious or you would like me to say a bit more about them, please ask me and interrupt me. So it should be more interactive than it's currently, but it's probably my fault. Okay. So I really tried to pick just the very central definitions. The point is, as I said, it's a vast topic, and you have to see. So I picked a few things which allow us to define central notions, function analysis, and we want to get some intuitive idea what's going on there. So again, here's definition. First of all, you probably know the Banach space is complete normed vector space. Space C. From now on, I will not always say over R or C, so it's implicit, and when in doubt, it's definitely over C. I may sometimes just drop this. So this means we saw Banach spaces already. Hilbert spaces are Banach spaces because they are complete in the norms. Okay, and now algebra, let's call this curly A over, once again, C. We assume that there is an identity. This is not essential, but it makes our life easier. So, an algebra with identity called 1 is any heavy machines coming through? Okay, so we have an algebra and it's called normed algebra such that, well, what do we have additionally in algebra, which we don't have in space? We can multiply, so the multiplication should behave well with respect to the norm. So we require the following. The norm of A times B is smaller than or equal to norm A times norm B. This property is called submodelity. For the obvious reason. Okay. And finally, if our algebra is a Banach space relative to this norm, then A is called, I'd hope that we have enough space here, but obviously not the case. Well, I put it here as a Banach algebra. So, question is, are the complex numbers a Banach algebra? Well, they actually are in whichever way, but basically they're not, because you need some way of multiplying elements, not just adding them. So, examples, well, we know examples actually, so let's first do this. Let x be. These examples are awfully important, they will show up again and again, so at least this example, we'll see this again. So this is a compact host of space. Everybody happy when I say things like compact host of space? Okay, good. So let X be a compact host of space, and let C of X denote continuous complex valued functions. Complex on X. Okay. So with which algebraic operations? Well, the obvious ones you take pointwise addition and multiplication. This becomes an algebra. So the question is, can we also give it a norm such that it becomes a Banach algebra? And the answer, of course, is yes. And norm is the following: equipped with the supremal norm, as it's called. Let's see, it's something very simple actually. Supremal norm. Norm of f is the supremum over all f of x. X in x. This norm c of x is commutative. Okay. just evaluate the function on all elements in your space and you take the supremum. Why is this? Why is this sensible to do? Well, it's a continuous function on a compact space. But this is actually the supremum is attained at some x. It's not really important. You can generalize this beyond the situation of compact house of spaces locally, compact house of spaces, and then you actually have to take supremum. But this thing exists, so every function in this space has a norm, and it's a commutative 100, which just means the multiplication is commutative. Is it clear when I say pointwise addition and multiplication? Okay, and then obviously you just multiply with complex numbers, and this means it's commutative. This is the prototype example for a commutative Banach algebra. It's also, later we'll have more structure, commutative C-star algebra. And in fact, all commutative C-star algebras look like this, so this is really an important example. This is something we actually use a lot in the Topos approach, but of course it's known for a long time. This thing that commutative C-star algebras are isomorphic to C of x for suitable spaces x that you can get out of the algebra. Okay, but of course we don't just want to do commutative stuff, we want the non-commutative Banach algebra also. And so example 2 is the following. I'll skip a minor thing here, which is not really important, but B of H, meaning the algebra of bounded linear operators on H. I say an operator on a Hilbert space means it maps a Hilbert space to itself. So this algebra is a algebra with respect to the operator norm. So let's look at this. Of course, the other really important example. First of all, how's this an algebra? So I can add linear operators. It's very clear if I take two linear operators, add them with another linear operator, I can multiply them with a scalar get linear operator. And I can multiply them, which is just composition. So it becomes an algebra under these operations. This is, of course, a non-commutative algebra because it matters in which order you compose operators. You already see this, say, with rotations in 3 space, which do not commute. And the operator norm gives us a norm, and then it turns out it's complete with respect to this norm. So we have a Banach algebra. And these two examples actually are really prototype examples. We will look at algebras with more structure than Banach algebras, having involution and having further structure, but they all turn out to be sub-algebras of B of H for the non-commutative situation, and for the commutative situation you can always go to a C of X. So these guys are important in that respect. Okay. I'm not claiming that every non-commutative Banach algebra is a subalgebra for P of H, but say once we have more structure evolution in particular, then we can show things like this. Okay, yes, now we can define the spectrum of an operator, and this is a generalization of what you know from linear algebra. In linear algebra you have a set of eigenvalues for an operator, and we want to generalize this to infinite dimensions, so we can't calculate characteristic polynomials anymore. But we can define it in a pretty straightforward way, and then we can at least, I wanted to say prove a few properties, but Okay. Another definition. So that's about the spectrum. So if A is element of a Banach A, we say that a complex number lambda is a spectral value for A. We'll say something on this in a second relative to the algebra. Why do we say this? What the following holds when A minus lambda, the identity. I start writing these things in operator form with hats, and the identity then becomes the one with the hat. So if this operator, which clearly is also in the Banach algebra, does not have a two-sided inverse in A. Okay, so when you look at this, you'll actually see, of course it does apply to the finite dimensional situation also. Is this clear? Is that much linear algebra still present that you see that you get an eigenvalue in finite dimensions from this condition? Okay, brilliant. Okay, but there's nothing which keeps us from applying this in infinite dimensions. The set of spectrum values is called the spectrum, of course. It's called spectrum of A, and we write this the following way: is denoted by spectrum. I have to put the algebra A here. And so I want to say something about this. Of course, this is a condition which refers to the Banach algebra in which we live. Now, this is something you probably won't know from physics. You always say the spectrum of an operator, and you never care in which algebra it lives. So why is that okay? Later on, as I said, we will have algebras which have more structure, in particular C-star algebras, and everything you are dealing with in physics is at least a C-star algebra. And there, the dependence on the algebra can be dropped, because if an operator is in a C-star algebra, it has a spectrum, of course, with respect to the C-star algebra, which is also Banach algebra, but it doesn't depend. You can go into another C-star algebra which contains the same operator and will have the same spectrum with respect to this other algebra, but the actual numbers do not change. So here we have to have this, but later on it will not be important. Okay. And yeah, well, I basically said this already. Of course, if you have a finite dimensional situation, you just get the set of eigenvalues here. And the interesting thing, of course, is that you can have operators in infinite dimensional situations which behave very differently. They have no eigenvalues at all, but they have lots of spectral values. I'll show you an example. I thought I would have enough time to go through this, but probably I haven't. So anyway, I'll show you the example. And it's quite interesting, actually relates to the position operator, if you look at it in the right way. So the example is, at the same time giving us another Hilbert space, that H be the Hilbert space of square. I may have to define this as everybody says. You should see this square triple functions on the unit interval. This is meant relative to the back measure. So we already had, but this was of course early on with respect to sequences, the notion of L2 spaces. So these are the little L2 spaces. They're also uppercase L2 spaces, and this is one of these. And the two is exactly this square integrable. And these are typical Hilbert spaces as they were. Well, they show up in physics if you want to talk about, let's say, a particle moving on a line or something. It's a bit odd that there's this unit interval here, but the algebraic structure doesn't depend on whether this is a unit interval. I can stretch it. But this doesn't really depend on this. What I wanted to say is the following. So we have this algebra, we have this Hilbert space, and now we have a certain operator. I think I'll write here, probably easier to read. And this operator is very simple, has no spectral value whatsoever, but the whole unit interval is in spectrum. So how's this defined? Let A be the multiplication, well, this sounds a bit mysterious, but I write it down in a second, and you see it's actually simple. Transform on 1. So this just means that well, A applied to one of these functions that we have there at x is nothing but x times the function. Okay, and physicists will see that this is the position operator. It's just a multiplication. Okay, so this is our operator, and the statement that I already made is then A has no eigenvalues, but spectrum, so let's be careful what you know is the H here. A is whole unit. And this can be found in Cadison-Ringrose. I will not have the time to present this. See Cadison-Ringrose, of course, volume 1, page 178. It's quite nice, it's pretty elementary to prove this, so it doesn't need a lot of machinery. And if you have such a situation, you call this a continuous spectrum for the obvious reason. Yes.
Is there a sense in which delta functions are eigenvectors of it?
Yes, that's exactly what people do when people talk about position. They want to have something like position eigenstates. Now, this is saying, and this is actually true in the strict mathematical sense, there are no eigenvalues, also no corresponding eigenstates. You have no elements in your Hilbert space, which would be eigenstates of this operator. It's easy to see. What you always have are approximate eigenstates, or elements in Hilbert space which approximate an eigenstate. And the limit then becomes, if you look at it in a suitable way, becomes such a delta function, well, which is of course not a function of distribution. And you're actually stepping outside of Hilbert space at this point. So there is a formalism in which you can deal with this. It's called rigged Hilbert spaces, and this is basically well understood, but it's out of the scope of what we want to do here. Okay. One thing I want to say about the spectrum is the following. Maybe actually we should take a break. Otherwise, we may protest at some point, which I would like to avoid. Or I mean, what's your? I would say 5 or 10 minutes. I mean, I can go on. I don't mind. It's not that I'm not exhausted, but I usually think it's a good idea to take a break at some point. Okay. Are there questions, by the way? So we're finally in a position to introduce adjoints. Again, adjoints of operators exist, which can be proven, and it's a non-trivial theorem that they actually exist. It's pretty easy in finite dimensions. You can actually show them explicitly, but in infinite dimensions you have to work to show that they even exist. I had hoped I could do this proof, but well, I could do it, but then we would spend today and next time probably at least half of the time next time. So I'll just tell you the theorem, and just saying this to remind you that the existence of adjoints is not a trivial thing. But once we have adjoints, we can then talk about many further concepts like self-adjointness, unitarity, normality, all these things. So that H, K, L, Hilbert spaces, if T is bound linear operator from H to K, then there is a unique element of bounded operators from K to H, so of course going in the opposite direction, and I should give this a name. So the element is written T hat star. Maybe people in this group would like to write me dagger here. Well, that's essentially what we call the dagger. Just following the convention in function analysis. So, what are the properties such that, first of all, for all x in K and for all y in H, we have that the inner product of T star acting, or T star acting on X, Y is X, Ty. So the usual thing, the idea is that you shift the operator from this argument to this, and then the inner product, and so of course they have two different operators, but that's the way they're related. But there's a lot more structure, which again later on will be generalized. So the structure itself will not be generalized, but we will go beyond the example of just bounded operators between Hilbert spaces. Concretely, we will go to C type class. So, AS plus BT. I'll say what ST and all the other things are in a second. So this is the bar over, these are complex numbers, the bar means a complex conjugate. So this is the first property, the second one is RS star is S star, R star, is TH star, star is H. Then we have and the C star property for the norm of T star is the norm of T. And when does this hold? S and T are bound operators from H to K. R is bound operator from K to L. And as I said, A and B are complex numbers. Okay. This shouldn't be surprising in any sense, but if you look at these conditions, as I said, we will see them again, and these are saying that the adjoint has all the properties of an involution. Later on we will talk about Banach algebras with an involution. These are C-star algebras, so this is directly abstracting from this. Having said that, we see that we have C-star algebras here. Well, it's not exactly true, because then we restrict to the situation when these Hilbert spaces coincide, actually, later on. Because, anyway, these properties are all familiar in some sense, at least from the fundamental situation. Yeah.
What exactly do you mean by D?
D is, okay, this is actually a very important property. This is the so-called C-star property. Maybe we don't call it at this point, but this is a condition which relates this algebraic structure of the involution to the norm.
Should it be T star squared at the end?
Yeah. Yes, I don't know what I wrote here, that's of course, sorry. Yes, I'm really sorry, this is complete nonsense. This is the right property, and I hope this makes more sense. Okay, with this in place, we can of course now talk about lots of more things. So first let me write down the name. So T star is called the adjoint of T. If you're deep into category theory, you may prefer to call this the Hilbert adjoint to distinguish it from adjoint situations and categories. Would actually be interesting. I didn't think about this. If we restrict to the finite dimensional situation, if we get categorical adjoints in some sense. So time's almost running out, but I think I can give it at least the definitions. So we have the following notions. H. Actually, I should restrict. Well, okay. You guys would call this thing the adjoint. Mostly in the literature, actually, one restricts the situation where T maps from one Hilbert space to itself. But I know in the group, because you're always talking about transformations between different Hilbert spaces, so maybe it's good to have this more general notion which exists after all. Okay, so now we assume that T actually has one Hilbert space to itself. So I say is called what is it called? It's called normal if T star T is T star. So if it commutes with its own adjoint, that's the notion. Next notion is self adjoint. If well T star equals T is called unitary if T star is T star T is the identity. So the adjoint is the inverse from both sides of T, and finally it's called positive if well, different ways of saying this. This is a way which does not involve anything but the inner product. So if this is larger equal to 0 for all x in Hilbert space. Okay. Normal operators are technically very important, but we will not talk about them a lot. Self-adjoint operators are of course extremely important in physics because they serve to represent physical quantities in quantum theory. So we'll have a look at them, and maybe let me just mention, well, maybe it's actually a bit more than a lemma. In finite dimensions it's a lemma, but in infinite dimensions we can call it a proposition, I think. But what I want to say is if I have again set T in H the self adjoint, then the spectrum of T with respect to B of H, which I have to say at this point, is a compact subset. Again, this is a bounded operator, a compact subset of real line. So if you look at this picture, here's the real line. So the spectrum of the self-adjoint operator completely lies on the real line, and then of course it lies between here and here if this is square. The norm of the operator lies on the real axis. Okay, this needs a proof. Again, it's not very hard, but it takes a bit of time to prove this. It implies immediately that positive operators are self-adjoint, because this is actually is an if and only if. I should say this. T be self-adjoint. How can I reformulate this? Get a different only if. Okay, just right. Right this way. Okay. So this then implies positive operators are also self-adjoint because their spectrum lies on the real line. Last thing I want to say today, and this is equally important, is you can see this as the first part of the proposition, and the second part is something about unitarity. So operator T is unitary. preserves the inner product. I sometimes say inner product, I sometimes say scalar product. I can't settle on one. It's the same thing. What did I say mostly? Scalar product. No, inner product. Okay. Anyway, you know what I mean. Inner product preserving. This gives an immediate idea what a unitary operator actually does. Because, let's say we have a Hilbert space, we have a basis, which means an orthonormal basis for us. Now a unitary operator acts, so it takes each basis vector to some other vector. First of all, preserves the length, because it's norm-preserving, so I get a bunch of unit vectors again. But it also preserves the inner product, and orthogonality was of course defined in terms of the inner product, which just means I take an orthonormal basis and map it to another orthonormal basis. So what a unitary operator does, it affects a base change in your Hilbert space. That's a very nice and geometric way of thinking about this. In many cases it's okay to think about this as a rotation. Of course there are also other unitary operators, reflections and stuff, which is also there, so it's not all rotations, but every rotation is a unitary, just not vice versa, but a large bunch of unitary operators from rotations. And that's, I think, a very good and geometrical way of thinking about unitary operators. Unitary operators also play a big role in physics, because we will look at, well, we probably won't, but people in physics look at so-called one-parameter families of unitary operators. And those are used to describe the time evolution of a physical system. So you have not a single unitary operator, but you have a whole family of them, and it's such that there's one parameter which is interpreted as time. So let's say you have, the last thing I say, I promise, is you have the following. You have unitary operators which carry an index t, which is a real number. There are certain continuity conditions, but the important point is that u0 is the identity operator, and then you move away continuously from that with t. And you can, of course, take this and let this act on the vector in your Hilbert space, which actually, I should also say, describes a state of your quantum system, and such your one-parameter family then takes the state to another state, so the state changes in time, and this is describing the time evolution of a quantum system. So all these structures that we introduced here have a relevance in physics. It's not arbitrary that I pick them, and try to get some idea across. Some technical stuff is necessary to understand it in any decent, serious way. Okay, I guess next time we will have to go on with this, and we will actually introduce C-star algebras, which are, as I said, abstracting from this situation, and talk a little bit about the representation of C-star algebras, and we'll see something that we saw today. I mentioned actually that these spaces, C of X, of functions of a compact Hausdorff space, continuous functions, they are very important. They are actually abelian C-star algebras, and all abelian C-star algebras look like that. We'll also briefly see how an arbitrary C-star algebra looks like, and then I'll say a few more things about von Neumann algebras, which are C-star algebras, but that's usually not the best way of looking at them. They have yet another structure. They have lots of projections. So actually, I wanted to say a few things about projections, but this can easily be part of another lecture, so probably I'll go on with these things. Okay, thanks for listening.